Good morning, everyone. My name is Ian Davis. I'm one of the primary support technicians here at GeoCue, and I will be taking you through our day one webinar or workshop for mission planning and flight operations. And tomorrow we will be focusing more on the software side of things, but today we're going to focus a little bit more on the hardware. As Brett mentioned earlier, you will need LP360 in the second half of our presentation today, where we're actually going to go through and process some data and function kind of like we are the flight operators out in the field, how to field check our data and things of that nature. So to get started, here's a breakdown of the material we'll be covering for today. So that's going to be our hardware overview. There's several different options out there: base station setups and requirements, checkpoint layouts and options, flight planning, flight operations, field checking your data, which is very, very important, and post-processing LiDAR data and doing your accuracy estimation. There are a couple of assumptions we make when you attend our trainings. The first is that you are or have worked with an experienced UAV pilot that is already familiar with some of these platforms and is familiar with survey missions. We also make the assumption that you have some kind of surveying background, so you're familiar with terms such as PPK, RTK, and the basics of a GNSS base station operation. Okay. So here we have a general breakdown of hardware that can be brought into LP360. You do have options for 3D and 2D scanners, depending on your needs. Here at GeoCue, we offer several different TrueView payloads with a variety of different scanners and levels of data quality and intensity, basically. You can get a lot more data if you go higher up, to say maybe our 600 series or 700 series versus our TrueView 1 Lite and 500 series, which is a little more manageable on your computers. As mentioned, you do have the ability to do 2D sensors as well, so that can be your DJI Phantom 4, your M300 RTK, P1 camera, and much, much more. Here we're going to go over two of our sensors general setup. So this is our 535 VC payload. This does have an APX15 board on it, which is going to be from the company called Planix Trimble. It does have a self-contained battery. This is one of the only payloads that does have that option, so you can have that additional power source if needed. It has three 26-megapixel cameras, and it has a HESI scanner on it that will allow for 3 returns during collection, which is very necessary for being able to do ground classification and other such methods. Here we have a breakdown of our 655, 660. They both have a very similar build. They just have a different APX board on them. It is going to come with a Regal Minivux laser scanner. It will have 3 20-megapixel cameras on it. This one has only the possibility for external battery power, so it has to be powered by your drone. And there's the ability to do your USB data transfer. So all of our payloads do come with their own USB. You will hear us also refer to them as a UMS. Now, these payloads can be integrated with a variety of different drone platforms. Just to list a few here that we actually test here in-house, that's going to be the Inspired Flight 1200A, DJI M300, M350, and now we have an M400. The Alta X, a BFD, Skyfront Perimeter 8, and the Harris H6 are some of the ones that are most commonly used. But if you ever do need a custom mount, please let us know and we will do our best to accommodate that need. So, like I said, your TrueView payload, when you purchase, will come with a mounting kit for your specific drone. Here we just have a quick little video of how to attach that, so we can provide you a copy of this if you would like it for later reference. And later today in our presentation, we will also be looking at mounting our payload and connecting to the Web UI, which is how you would actually manage your data storage and the start of your missions, things like that. As you can see, when you are mounting the bracket to the payload itself, it will come with all of these different components, including Loctite. That is incredibly important to use when attaching the mount because it ensures that vibration does not interfere with those screws and maybe making them come loose. So that way you don't have to worry about any vibration interference there. So that is a very important component. As I said, all of these components will come included depending on your specific mount. So this is going to be an M350 that you're seeing here, but all of the drones I mentioned previously will have their own specific mount setups. It does include these little handy cable ties that you're seeing here that can actually stick directly onto your drone that helps keep from having the cables like fly around and potentially getting caught in the propellers, which would be a very, very bad experience for everyone involved. So we do make sure to include some of those for you guys. After that, the installation of your payload is very easy. You simply pull out that little tab that you see there until you see the red. You make sure that the payload is flush with pegs inside its little holes, and then you push the tab in until the red disappears. Again, this will be covered later in our presentation where you'll actually get a hands-on experience with that. Okay. So as I mentioned, this is going to be what's called a PLI mount, which allows for a quick and easy installation. As you can see here in our video, it takes only a matter of seconds. You do want to give it a little wiggle test after you attach your payload. If not, you may end up not having the pegs all the way flush. So that's just a way to make sure that it is fully attached. You do want to make sure your payload is aligned with the front of the drone. That is very important to make sure your data is collected in the proper fashion. Like I said, push the payload into the adapter slots. There will be 4 individual pegs. You do want to make sure those are flush with the bottom of the mount. For data storage, as previously mentioned, you will get a USB included with all of your purchases of a payload. This is going to be a 32 gigabyte USB that also has safeguards against EMS issues, so you can actually insert it into your payload before flight, and then you can fly with that in tow. It is going to be a FAT32 format that is required if you ever decide you need a bigger USB for data transfers later on. One, you cannot fly with those, only fly with the EMI safeguarded ones. And you do want to make sure those are a FAT32 format to ensure data transfer. It is possible to fly without the USB installed on your payload. There is 128 gigabytes of storage on all of our payloads, so that's internal storage. So this is actually recommended for endurance flights. So if you're going to be out there collecting a really large flight, it'd probably be better just to transfer at the end. If you did decide to fly without your USB, all you would need to do is land your payload, power it off, insert the USB, power it back on, and data transfer will begin immediately. All right, so base station requirements. So TrueView payloads use PPK solutions. There isn't an option for RTK. So GNSS signals must be recorded during the entire duration of the flight. Now, for our payloads, we have 3 different options for processing, especially for those APX boards. So the first option is going to be what's called single base. Single base is if you have your own base station, or you're also using a local core station and you're able to go and download that base station observation. The second one is going to be SmartBase. SmartBase is a virtual reference station that is actually using the core's networks. It will do triangulation between the nearest possible networks and will work as a functional backup if anything goes on. This does require LP360 points, so do keep that in mind as it is a paid subscription. Same with the Trimble Centerpoint RTX or PPK, apologies. PP-RTX. It is another paid subscription. This one has virtually 100% coverage throughout the continental US. So if you're ever out in a rural area, since both of these are paid services, it might be better just to go with the PP-RTX option versus SmartBase to ensure you have coverage. All right, to actually go through our different requirements, if you are running your own base station, there is requirement for the L1, L2 satellite support there, or L1, L2 support, a minimum of GPS and GLONASS constellations must be observed in your observation. If you are using your own base station, it either needs to be in a RINEX format or it needs to be in a TO1 or TO2 format to be imported into LP360. It will not recognize other formats. For your base station, you do need to make sure you have a latitude, longitude, and ellipsoidal height coordinate for that particular location. If you do not have that, you can run it through OPUS to generate that information. You'll need your antenna height, the manufacturer and model supported by POSPAC UAV, or if you're using one of our TrueNav payloads or CHT, we can talk to you about those other details. You do need the input reference frame used when you are collecting your base station. This is highly important that that frame matches what your project is in. If they are different, you will notice your data set will appear in a different location. And it's just because it's using two different coordinate systems. It is also important that your base station is recording at a 1 hertz interval. That's basically a 1 second interval is what it needs to be recording at. As mentioned, you can submit your base station off to OPUS to get that static location, so the latitude, longitude, and ellipsoidal height. We'll actually talk about how to do this later on. I think we typically do this on our day 2, but I will reference it throughout our exercise later today. There's also options for Australia, Canada, and some other places like that. Okay. All right, moving on to our control points. It is very important that you make conscious decisions about the placement of your control points. So first off, you do want to make sure that they are on the interior of your flight lines. So if we look down here, these are on the interior. Nothing goes on the outer edge. If you put it out here, you're far less likely to get sufficient coverage to get an accurate representation of that target. You do want to also make sure that you have points at the corners of your project, so that way you can get global estimation of the accuracy. Other points can be distributed evenly throughout the project after that. You do want to try and make sure your points are visible in several different images, because you can actually use those to help pinpoint the center of your target if you're needing to use what's called measure mode or something of that nature. Let's see. If you have a project with significant variation in your elevation, it is very important that you have a target at each of these elevation points. If not, you may end up missing some of the estimation, or there may be something in your trajectory that could impact those areas. So you want to make sure you have a representation of all of those surfaces. You do want to make sure your control points are on smooth, level surfaces to the best of your ability, and you want to make sure there's no vertical objects near them. So no buildings, no berms, vegetation, things like that. So you may want to flatten out grass or move it away from some trees or things like that to make sure you're able to get accurate measurements on these. We have a couple different target types that can be used in LP360. So we have a 2D ground target and a 3D ground target. Both of the ones we're talking about today can be used for 3D estimation. So these 2D targets are going to be a flat checkerboard or a concentric circle. The use of the black and white colors actually allow us to estimate the centers more efficiently in LP360, because the intensity values are actually measured by the laser scanner, not by the camera. So you're getting a more robust measurement. Like I said, it will estimate the X and Y, but it will do an interpolation of the Z value over the entire target using the nearest neighbors and versus picking a single point in the center of the target, because LiDAR data is inherently random in the way that it is collected. It is sprayed out and can vary depending on your surface, depending on your speed, your flight pattern, things like that. So you may not always get a point directly on the center, which is why that interpolation is very important during this process. 3D targets Here at GeoCue, we actually offer what's called an accuracy star. So this accuracy star actually has 6 reflectors out on these little arms that allow for a more robust measurement. So you could actually use less of these types of targets than the 2D, and you could still get the same level of accuracy, same level of measurement there. You would place the GNSS antenna at the center on the top up here to get that measurement. You do have the ability to connect a GNSS receiver on top. You would install this typically over a survey nail or some kind of monument to get that measurement. There will be vertical separation between the survey nail and the reference height of the particular accuracy star, as you can see here, but there is something called an H offset that you can actually estimate using a tape measure. We have a quick little video of that that'll come up, and that will actually be put into LP360. That way it can compensate for that height difference. So there are a few advantages to using the accuracy star over the 2D targets. So one of the most important ones is the fact that it is very accurate because it is able to utilize both robust and precise measurements because it has multiple reflectors. So even if you only hit, 3 of these, as long as they're on different ends of the star, you will still get a really good measurement from here, especially because it is a fixed length for all components of this particular accuracy star. The next one is that it is completely separate from the underlying terrain. So if you have somewhere that's very muddy, you have somewhere with a lot of tall grass, anything like that, you can still get a very accurate measurement doing this versus if you have your 2D targets, you'll have, maybe your target sinking down into the mud. Maybe you have grass trying to come up over your target, things of this nature. So this is incredibly helpful for those more rugged terrains. It is important that if you are using an accuracy star that you are installing it at the highest possible elevation from the ground. So that way you can make sure it has that complete separation and get those measurements. So the only thing that's really going to impact the detection of these targets is actually going to be your flight parameters. So if you're flying really fast, maybe where you place these. So if you put it on those outer edges, you might not get as good coverage on those. Or if you put these near like a turn, because you will change your speed as you approach a turn, that can end up causing the sensor to tilt and you may not get quite as much density on top of those targets. So as I mentioned, it is completely independent of the underlying terrain. The accuracy star could be over a gentle sloping area, those wet or dry locations, somewhere with a lot of grass. None of those will impact the measurements on top of the accuracy star. So this is very, very helpful. Again, the flight parameters are what are actually going to impact your quality of detection of these targets. So speed, height, motion. Okay, so trying to put those a little bit more towards the interior, not near your turns, is very important to make sure you get an even point density over the top of these. If you're interested in global accuracy using this particular target, you do want to make sure that you have those distributed over the entire survey area. So as I mentioned earlier, having them all at the corners of your project would be very helpful for this. If you're more focused on a local accuracy, so let's say you're flying over a large area, but there's some monumental environment towards the center. Maybe it's a neighborhood, maybe, it's a power plant or something like that. You could focus those stars a little more localized in that area to ensure you have the best level of accuracy. All right, so here we have a quick little video just to kind of demonstrate what it looks like to set these up. So you would need a tripod, but everything kind of screws together, pops in place. It does come with these little magnetized reflectors. So all you have to do is pop them on, they'll pop right off. And it also has this little magnifying glass to see the survey nail underneath, and it has a little level on it too, so that you can make sure it's nice and flat. That last little measurement there is where he's actually getting that H offset, and those can be done very quickly, so you can have this up and ready to go in less than 5 minutes. All right, so now to talk about the basics of mission planning. So quick little note here, you will notice that I have a link down here. We have an entire mission planning document as well as a spreadsheet that is incredibly helpful for identifying the parameters needed for your specific mission, including if you're having to plan around vertical objects. So we do have that fully available to anyone that needs it. All right, so line spacing. This is going to be the distance between your flight lines. It is very important that this is taken into consideration to avoid data gaps. So if you know you have some kind of vertical object that'll be in the center here because you're trying to get overlap on both sides, so just getting basically extra points on that target, you do want to take that into consideration, maybe making that line spacing a little bit smaller so that you get more coverage, things of that nature. This number is dependent on the combination of flight height, scan angle of your particular sensor, and the percentage of side lap that you would like to see. That is also referred to as overlap in those areas. Again, this is all in that spreadsheet, so you can play around with those values, and it can help you identify the ones that'll work best for you. Okay, for our flight altitude, you do need to make sure you don't exceed the maximum range of your LiDAR payload, especially if you're doing terrain following or something of that nature, because if you do have, let's say, a valley that you're flying over, hold on just a moment, guys. Okay. If you're flying over a valley or something like that, and you are not following the terrain, you may end up noticing that down at the bottom of the valley, you're missing a lot of points, you're not collecting. That could be because it exceeds the range of your LiDAR, so do keep that in mind. If you're flying at a lower altitude, you will have a narrower swath, so less coverage, but you will have more density in that point cloud. The typical recommended altitudes that we see here, that we typically use, is going to be about 80 meters for the 500 series payloads and 100 meters for the 600 series. All right, scan angle. This is going to be the angle off of nadir at which your LiDAR will be clipped. Now, for most TrueView payloads, this is going to be 40 degrees, which means in total that is 80 degrees below your payload. This can be increased to a certain extent, depending on the payload itself, to produce a larger swath, but at those wider angles, you may get what's called bad incident angles out at the edges, so your data will be less accurate. So we typically want to recommend to stay within, these parameters here. The only one I can think of that has a smaller scan angle off the top of my head is going to be the 540. That one, I want to say the clip angle is 35 or 36, so roughly 70 degrees versus 80. All right, lateral overlap. So this is also referred to as the side lap. This is going to be where you're getting those overlap in between your two flight lines. Now, this is used for flight line alignment later on. So this allows to make sure your data is properly aligned using our strip align tools and things like that, because there can be dynamic error detected in your trajectory, maybe due to movement, maybe wind, something like that during your flight. And having this overlap is really, really helpful for making sure your point cloud is accurate. So you do want to make sure that's in there. Also, when you are trying to collect a point cloud for vertical objects, you typically want those planned in between two flight lines because you want it hit from both angles, so that way you can get a true representation of the vertical object and not just have one side of it. Okay. As I mentioned, this will increase your point density in those areas. So objects of importance typically want to be in this area. That's also a great place to put your targets because you are getting a measurement from both of these and you're far more likely to be able to detect the full target. 50% side overlap means that the spacing between your flight lines will be covered twice from both these angles. Like I just said, that's just a rephrase of that. But another thing that can provide a margin of error is not just your flight parameters. It's also going to be variation in the terrain. So you do want to take all of this into consideration when planning your flight. So terrain is very important. Now, especially considering vertical objects, we have what's called a data holiday. This is where you are missing sections of your data. Now, what we see here is we have this canopy, we have our scan angles underneath our flights, and then we have these little spots here that just seem like they're missing something. That is because the flight parameters did not allow for us to capture this portion. Okay, so that's why you want to take vertical objects into consideration when you are planning these, because I've seen this happen many, many times with power lines, with canopy, with buildings, and then you have to go out and refly. Okay, so that ends up wasting resources and time. So definitely take a little while and use this spreadsheet. You know, we do have it freely available at any time to help you plan those parameters around your vertical objects. Here's an example of what that spreadsheet will look like when you are trying to plan that vertical space. So you can actually see right here, this is the vertical surface. So that would be whatever you're trying to measure. You can input that in and it will actually spit out a bunch of parameters for you. All right, so we do have some general recommendations for our flights. So a general purpose, maximum coverage, and thick canopy. So for your general purposes, you'll have that 40 degrees field of view. You'll be flying at roughly 60 meters in height. That's typically what we do here at GeoCue at our headquarters. We'll do 60 or 70 meters. That will give you about a 100-meter swath underneath each flight line. We're going to do a 25% side lap with a 75-meter line spacing. So you may notice that we do a lot of stuff in meters here. So if you are using feet, do take care in converting those values when planning your missions. For maximum coverage, you'll notice that we do open up that scan angle or that field of view by 10 degrees. Remember, this is entirely dependent on your payload. So make sure you look into the coverage or the field of view of your camera and your LiDAR. So for instance, the 540, the reason its clip angle is 35 degrees, 36, is not because the LiDAR will not collect. The LiDAR can collect many more points on the outer edges. However, the camera cannot colorize those because there's only one singular camera right below the payload. So if you open it up more, you'll have uncolorized points. Okay, so do keep that in mind when you're checking these. For that maximum coverage, you will increase that flight height up to 75 meters, which will give you a wider swath. You will also use, for that same 25% side lap, you'll have a larger line spacing, so that'll be 135. Now, this will mean you will have less density in your point cloud than the general purpose. Now, for the thick canopy, and this applies to any kind of vegetation, you probably want to fly lower. So you can see we actually cut that flight height in half. We actually trim that field of view down to 30 degrees because we want to be a lot more localized in our points. We don't want bad incident angles. And we're going to have a much smaller line spacing. Typically with thick canopy or with vegetation, you're also going to want to do a crosshatch pattern. This allows you to have more likelihood of penetrating that canopy to reach down to the ground because you'll be hitting it at different angles in that crosshatch pattern versus if you just go in one direction. So we also have these lookup tables that are inside that spreadsheet that I mentioned earlier that will give you recommendations for your scan angle of your particular sensor, the altitude, and things of that nature. So you don't have to go out there and guess what parameters will work for you. We will give you, everything that you need for success in that mission planning process. We do have one specific to each payload. So if you open up that spreadsheet, I'll even open it up in just a moment. That way you can see it. But it will have a tab for each payload that we have. So that way you'll have unique flight parameters for those. So here we do have a quick little video about how to plan a mission with a custom camera inside of DJI Pilot 2, because the DJI drones are some of the most common that we see here. And this is also a very user-friendly way of planning your mission, which is why it's one of the most common. I will let this video run through, but then once it's finished, I'll actually go ahead and open up that table for you guys to take a look at. So you can actually see we have some mission plans that were already imported in, so the field of view and things like that. And what I really like about this is you can literally modify your speeds, your course angles. You can actually drag your boundary around and it will actually adjust your flight lines to what will fit your needs in this particular area of interest. So it is very, very user-friendly. Now I am going to pause this for just a moment. We'll come back to everything else in here where we talk about the web UI, but just so you can take a look at that mission planning spreadsheet. So this is what it looks like. As I mentioned, there is a tab for each one of our payloads down here. So the one I'm looking at right now is for the TrueView 1, but we can find one for the 540. It will also have all this helpful information over here. And then if we keep going over, you can talk about spot size for the different types of scanners. So we have a lot of information in here. But we also have that entire tab dedicated to vertical surfaces. So buildings, canopy, power lines, things of that nature. All right. So now to start talking about getting into our data collection. With our TrueView payloads, you can connect to what's called the Web UI. This provides a user interface for you to interact with your payload that is connected through any web browser using an internet connection that's actually provided by the payload itself. So this is used for monitoring your system operations, if it's ready to collect the data, you can change settings in there, and you can actually check on your storage. So if your UMS or USB, those words are interchangeable, you can actually ensure that you do have enough storage space before you start a flight, and you can see how much of your internal storage is being used on your payload at any one time. Again, since this is monitoring the status of your payload during operation, it is also incredibly helpful for troubleshooting any errors that may occur. Okay. All right, so to establish the connection to this, you will do a internet access option there. You should see that it says payload underscore and the serial number of your payload. All the passwords for this will be the same. It's going to be TrueView, all lowercase, no special characters, and you can access it through any browser using one of the two URLs listed here. I want to say for my iPhone users, Android, I think it's Android, you might have a better chance using the 10.0.0.1 to connect. But in a moment, when we go and check out the hardware, we will get you all to connect to the payload. That way you can actually see what that's like, get a feel for the settings and things of that nature. If you do notice that your browser fails to load the URL, it could be because it is defaulting to this HTTPS when it needs to be an HTTP. Okay, so that's just a quick little thing. We've seen this happen many times, so just be aware of that. As another quick note, you will get a PDF version of this PowerPoint at the end of our workshop, so you can always come back to this for reference. All right, so some of the settings you can modify in the Web UI. That's going to be your payload profile. This is going to be a unique profile for your payload and the drone configuration. This also applies to anyone that may have a mobile mapping unit out there. There will be a specific configuration for that and for the antenna that's used, just in case you're using some different antennas. You can modify if you would like to save directly to the USB or not. This is something that can be enabled or disabled right here. If the option is not displayed, that means this particular sensor does not support that feature. Okay, so we do have some older sensors out there that don't have that possibility. You do have what's called proximity mode. I highly recommend having proximity mode enabled. So it actually, when this is enabled, will create what's called a home point when the payload is powered on. You can kind of imagine around this home point that there is a bubble. So in this case, we have 25 meters. So that means if the payload is within 25 meters of that home point, it will not record data. So if you are starting the mission, you will need to exceed 25 meters. It will then start recording. That way you don't have a million pictures of you taking off. And it will actually start downloading the data automatically when it re-enters that bubble. It'll start transferring it to the USB automatically if it is inserted. You can also modify your lever arms. That's actually what's stored in this payload profile. The lever arms are the specific values for your drone, antenna, and payload configuration. So if you have multiple platforms, you will need multiple payloads or payload profiles in this instance. Okay. You also have the ability to do what's called a pilot logbook. So this is entirely optional, but it will be stored along with your system folder information. So we do have a little template that you can import right here, and that just allows you to enter in information like the date and time, the mission type, ground conditions, weather, things like that that you may want documented alongside your data collection. Again, this is entirely optional. You don't have to do it, and you can always fill it out later because all it is a text file that is created and then added into the system folder of your raw data set. When the cycle is complete, you will see this little messaging up here. So it is completed and ready for shutdown. That's after the data has been transferred if you have the USB inserted before flight. And that way you'll know exactly when the payload is ready to start shutting down. It will initialize that on its own after it has cleaned the internal storage and things like that. If you do not have the USB inserted, you would notice that it will just say it's ready for shutdown or things of that nature. It's done collecting data, power it off, insert your USB, recycle the power, which means turn it back on, and it will automatically begin that transfer process if it detects a cycle on its internal storage. All right, so troubleshooting. So not only does this give you a full system log right here, older messages will be at the bottom, newer messages will be at the top, but it will also actually colorize the top based on the issues it's experiencing. So for instance, the APX, that's going to be the board that is internal to your payload. So typically that one's always going to be green, but if not, it will let you know. You can see the GNSS, so that's actually your satellite connections. This one is actually red. So that indicates we're having some kind of issue. We know that it's something to do with our satellites. So maybe there's a vertical object near us that's interfering. Maybe there's an issue with the antenna, things of that nature. So we know what we're troubleshooting. If you ever do have continued issues with your payload and you need to reach out to us at support, you do want to make sure that you take a screenshot of this messaging that you're getting. That way you can provide it to us, and there might be some nuanced messaging inside of the status log that will help us understand what's going on so that we can better assist you. Something else you may notice as well right here, it's going to be highlighted in yellow. So everything appears green, but it's still giving us a message. That's letting us know that the external storage or the USB is full. So we would need to remove the USB, remove some data from it, and then reinsert. When you are plugging in and removing the USB, you do want to make sure you power off the payload. That way you're not pulling it out and potentially corrupting some of your data. So do make sure you shut that off before you do that. All right, system management. So all of our payloads will come with a multifunction button and some LED lights. Now, these lights can be used to monitor the status of the system. So on the left-hand side, when you're looking at the back of the payload, will be your system light. The one on the right-hand side will be the APX or the satellite connection. And the multifunction button is for turning it on and off. Now, even though these LEDs are here, I strongly recommend using the Web UI because you're going to get a lot more information about what's going on versus if you use these LED lights. Now, if you do decide that you would like to watch these LED lights, or maybe you're looking at them from a distance or something like that, this is going to be a general LED light sequence guide that we have here, but for each of your payloads, there may be a slightly different configuration. So you can also find a sequencing guide inside of the hardware user's guide for your particular payload. All right, so a few notes about flight safety. So the first one is flight operations of the TrueView 3DIS surveying systems. They must follow best practices and safety regulations for commercial UAV operations. Okay, we strongly recommend this. This is something that is required. All local and regional flight requirements and airspace regulations must be adhered to. Any specific regulations related to the use of a LiDAR system on a UAV must be followed. Okay. Finally, all of our TrueView payloads do have EMI-safe Class 1 LiDAR systems. This means that it uses the near-infrared wavelength, so you can fly over people as long as you are within regulations. You have the proper waivers and everything like that, and it will not damage anyone's eyes. If you are using something other than a TrueView payload, you do want to look into that if it is eye-safe or not, and be very careful in use. All right, so we do have a general checklist here. We are going to go through all of this out in our workshop in a little bit to take a look at one of our hardware components, and one of our flight operators is actually going to take you through this. I'm not really going to dive through this in our presentation today, but again, you will get a PDF version of this, and you are more than welcome to pause our video for today and take a screenshot. So this is also included in all of the hardware user guides for every sensor that we have. Okay, something else that is important to consider when you are flying your own missions is the KB index. KP. Why does that say KB? KP index. So this is a forecast for monitoring activity on the surface of the sun and can impact your quality of your connection because the solar activity will impact the Earth's magnetosphere. That is a big word, so I do apologize if I stumble for a moment. There are some times when these particles are emitted, maybe during like a solar flare or something like that, which is why you want to monitor this, that will impact how you connect to satellites. So if the KP index is at or above 4, you probably don't want to fly. Because if you lose connection with your satellites, if you lose connection with your payload, you are more likely to get into a crash. We don't want that to happen. We'd rather you stay safe. We'd rather you have a payload to continue using. So do keep that in mind. We have a couple links here on where to go find those. You can look up the 3-day forecast from NOAA. So the NWS Space Weather Prediction Center. You can look that up at any time. And then if you just need some additional information, you can look up the space weather and GPS systems for NOAA as well. All right, something else is if photos are important to you, you do want to take into consideration the angle of the sun, and you also want to take into consideration cloud cover and things of that nature. So once again, if photos are important to you and you are wanting to get good quality photos with no atmospheric haze, you do want the sun angle to be at 30 degrees or greater. These will be the most suitable lighting conditions for obtaining photos. If your angle is lower than this, you may end up experiencing hazing photos. You may experience more shadowing and things of that nature. Quick note with this too, if photos are not important to you, you can fly at night. As long as you are following all safety regulations, LiDAR will continue to collect. Light is not necessarily necessary for LiDAR since it is using a laser. This is only necessary for photos. All right. So before a flight, again, we will be covering this with our hardware out back, but I will go through these really quickly. So first off, you'll start by powering on your system. You're then going to want to connect to your Web UI. That is the very first step after you have verified that your hardware is safe. You will notice that the LEDs are flashing yellow. You will also notice in the Web UI that it is letting you know that it is initializing. So you should see those in both locations. I'm going to kind of disregard these here because I would much prefer you watch the Web UI to verify when your system is ready versus the LEDs, especially if they, degrade over time. They're not quite so bright, or maybe it's really bright outside. You might not be able to see them. When you take off, you do want to fly to a safe altitude. Typically, you can fly higher than your flight height. That's perfectly fine for your mission plan, but you do need to perform what's called the heading alignment maneuver. Now, this is incredibly important that it is performed for every single mission. This will prepare your IMU for data collection. After that, you can then engage your mission and go throughout your flight. Now, to talk about the heading alignment maneuver, this is different for the TrueView 540. So if you are out there using a TrueView 540, you'll be doing a figure 8. But for our other TrueView payloads, this is going to be the heading alignment maneuver that you will be using. This is also referred to as the ham movement. So if you ever see that abbreviation, it's talking about this particular maneuver. So when you get to a safe altitude, you're going to perform this before and after your mission. You will want to push the stick forward quickly and hold until your drone accelerates to 10 meters per second. So watch on your RC till it hits that 10 meters and stop. This typically takes about 4 seconds. You do not want to put in any other inputs. You want it to be a straight line. After that, wait about 2 seconds and yaw your payload slightly, so 15 to 20 degrees, because you do not want it flying back at you. And then you will repeat the process in reverse. So you'll actually pull your throttle back until it accelerates until about 10 meters per second, about 4 seconds, and pause for just a moment and then engage your mission. Now, if you are accelerating, you do want to keep it close to 10 meters per second. Try not to exceed 14 meters per second, as this can jostle the IMU a little too much, may cause a little bit too much body acceleration, and it may impact the quality of your collection later on. So do keep that in mind. All right, so after your mission, you will want to fly back to your home point, but do not land. You again need to perform this heading alignment maneuver before bringing it back down. If you are in proximity mode, once you enter that bubble, so that 25 meters that we saw earlier, it will automatically begin the wind down and data transfer process. If you don't have proximity mode on, or if you have to land outside of your home point, so say maybe your battery started dying, you had to land at the other end of your mission site or something like that, you will have to manually shut this down. So once you land, you would press and hold the multifunction button on your payload and shut it down. If you have a USB inserted, make sure you connect to that Web UI and monitor the status before you power it down manually to ensure your data is able to transfer off successfully. If you are monitoring those system lights, so, here it will tell us if it's ready. If you're looking at the system lights, they will turn a solid white color when they are ready to be shut off. So once this is all complete. So field checking your data is incredibly important because we don't want you to have to go out and refly just in case something did happen during flight. So if you lost connection to satellites, something of that nature, you can actually perform what's called a QC-only real-time trajectory report. So this does not process your trajectory. This only displays your trajectory. So you're able to check it throughout the entire flight. This is performed directly on your computer, so it is run locally. And it does not require any additional licensing and no additional files. You just need the raw data and you just need your computer with this installed. Now, again, the results from this are not processed, so they are not applicable for final product delivery, but you can actually generate a point cloud from these, so that way you can verify that it's covering the area you expect it to and that colorization appears the way you expect it to. So that's a quick little check you can do. We do have an entire sheet dedicated to the different field checking methods that we recommend. And again, this PowerPoint will be provided to you after our presentation so that way you can come back and check any of these links at any time. All right, so when you're reviewing your trajectory report, there are several different spots that we're going to stop in and review later on in our presentation today. This just kind of highlights a few of those key points, but typically this is going to be after you've run your SmartBase, single base, or PP-RTX when you have all this additional information. Typically what you would be looking at for just the QC is just these first little bullet points here. Now, we do have 3 different trajectory processing capabilities depending on your particular payload, so we do have a reference here for those different reports. Okay. Inside of LP360, you also have the ability to archive your data. This works as a functional backup, and we strongly recommend that you do this while you're out in the field. That way, You can not only have your original copy or whatever you put into LP360, but it'll also create a zipped archive for later storage. And LP360's archive manager, so that archive function, actually utilizes what's called robocopy. This does an integrity check of your data before and after the transfer to ensure that nothing occurred to corrupt your data in that transfer process. Here at GeoCue, we also use what's called TerraCopy whenever we're copying files or projects or something like that. So we also strongly recommend that you get that installed on your computer because, again, that will do an integrity check before and after you transfer your data set to ensure they are the exact same. The Windows copy tool does not do this. Okay, so do keep that in mind. So today we will actually go through setting up our archive, how that works, what it looks like, and things like that. You can also archive flights and push them up to the cloud if you needed to, if you have cloud storage available to you. We actually have 2 sample data sets that we will be using today because I think they mentioned to us it's a little too windy. We might not be able to actually go out there and collect data today, but we'll still go check out the hardware, get it set up, and things of that nature. We do have a workflow dedicated to cycle recovery, just in case maybe you had a premature shutdown or something like that, and part of your cycle did not transfer off of your payload. So to do that, again, you do want to make sure you're monitoring that log status at all times through the Web UI. You would recycle the power to the system. So, if you need to turn it off or turn it on, depending on if your USB is already inserted, make sure it is fully inserted into the payload. You can either watch the Web UI and ensure that the data copy is successful, or you can wait for the solid white system light. So this is the light on the left-hand side of your payload. And once it has finished that process, you can shut it off, take out the USB, plug it into your computer, and you should notice that there's either going to be a debug log at the root level, or you can find it in the system folder of your cycle. Now, these logs can actually be provided to us at support for us to troubleshoot what happened, maybe why that issue occurred, and help prevent it from happening in the future. Okay. Now, do keep in mind that if an accidental power down does occur, that the TO4 file, so your trajectory file, the one storing all the location information, is the last one to be transferred. So if that file is not able to successfully copy off of the system, that can either be because maybe you don't have enough storage space or something like that, you will need to go back and recover that using this workflow or a separate one to pull it from the APX if needed. That is a very, very niche and not common practice. All right, so as I mentioned, there's several different payloads that can be used in LP360 that may have some different workflows, so such as the TrueView Go and the TrueView 540. The TrueView 540 actually mirrors that of our other payloads, but there are a few nuances that are a little different there. You can also process DJI L1 and L2 datasets. The photogrammetry payloads that were mentioned at the beginning of our presentation today. And some users actually like to import their Wingtra or other sensor data into LP360 for additional processing. So photogrammetry, classification, things of that nature. So there's a lot of stuff you can do with LP360, even if you don't have one of our payloads. Does anyone have any questions on the information today? I know I threw a lot at you, so I don't expect you to remember all of it. I will be going over a lot of it again. All right, so if we don't have any questions, we can take a quick little break, and I'm going to go make sure that we are set up for us to get back there and have you take a look at one of our payloads.